Hi, hello, how are you doing? I hope that you're doing just fine or even better. And I want to start with a few questions. So, how fast is it? How fast could it be? And how fast should it be? No matter if you write software for a cloud environment or on premises, these questions might eventually pop up in your head. And are they truly important? Should they always be answered? Let me give you a few hints related to these questions. My name is Szymon Kulec. I work for Particular Software, delivering a service bus and the platform behind it. And I want to encourage you to join me in this journey through various aspects of performance-oriented software. So let's start with that thing that I called perfect performance. And it's 4 p.m. already, so it's easy to imagine that you're lying on a couch. It's quite cozy, it's quite comfortable. And then an idea pops up. Basically, you think, oh yeah, in this first example, I could replace these string allocations with a string builder. Or in the second one, you could think that let's switch from a list to an array and skip the link use statements altogether. And I'm not talking about thoughts being a result of like a long profiling session. I'm talking about these ideas that hopefully change your performance of your application without any measurements at all. And this is a really bad case, and probably everyone in here had at least one of them. I must admit of several ones. And the idea is that it works in the following way. You look at this code and then something pops up. And this something is quite often wrong. And by wrong, I mean that the same rule that can be applied to a gym or to a workout could be applied to the performance as well. And the thing is that you should measure your gains. And if you want to measure your gains, first, you need to measure the current state of affairs or the current state of your application. And this could be done by running a profiler, or this could be done by writing a test with a library like benchmark.net. And the additional thing that you could move forward with would be to put this test into your CI environment. And basically, once the threshold of your performance is breached, then it would make your build a red one, or mark it as a red one. Additionally, if you go below the specified threshold, then it would make it green again. And actually, it does not matter which managed language do you use. Is it Java, Scala, C#, F#, or if you are brave enough, Visual Basic.net? Unfortunately for the creators of these frameworks or languages, and fortunately for us, the list of the optimizations you could come up with overlaps with the features of these languages or the frameworks. And this could be things like allocations, copying stuff over and over again, and all the bytes management done wrong. And this was the case in these following two examples I want to share with you. The first was based on Martin. That's the .NET library built on top of Postgres, providing some document DB-like capabilities. The second was strongly connected with akka.NET. So let's start with Martin. Martin is a .NET library, as I mentioned, built on top of PostgreSQL. It uses an extensively Postgres JSON support. So internally in Postgre, that's the JSON B type. And capabilities provided by the .NET driver or the connection provider. And the name of it is like the NPGQL, I believe. And it's funny that the creator of this library, Jeremy D. Miller, you might have heard of him because of the structure map or REPL, like the good old-fashioned NuGet package manager. He came up with this name basically by Googling for natural raven predator. And I think that you can connect the dots with the document database. So Marten provides two main capabilities. The first is the regular document database. So you can put a document into it, you can query for a document, you can commit multiple changes across different documents within one session. So that's the first one. And the second one is the event store that actually allows you to work with like a regular event sourcing. So you can append events to some streams, you can query for them, also some support for projections, views, of course asynchronous is provided as well. So as the Marten's primary data format is JSON, you can imagine that one of the core components of this library is the abstraction over serializer. And as you can see in here, there is that serializer interface that is used basically for anything. If you store a document, if you append an event, whatever basically is stored with Marten will use these methods. And there are two methods in here. The first one basically stores additional metadata. The second just skips them. But as you can see, both methods work in the same manner. A document or any object is passed to them, and then a string is returned. So of course, yes, strings are cheap, but as the old performance proverb says, if you can skip doing something, it will be basically faster. So if you could skip doing something in here, what would it be? Formatting, okay. Some other ideas? That's correct, yeah. Basically, just removing the allocations. Okay, but if we wanted to remove the string allocation, we would need to provide another way of actually storing the serialized content of the document or an event or whatever is stored. And so the choice was simple. Basically, introduce an overload that will take the same argument as the methods mentioned before, but as an additional one, you would pass a text writer. Text writer is like a good old-fashioned class in .NET, which is capable of writing text. And if that was the only change, of course, it would not work, because underneath the text writer still needs to allocate some stuff, right? So instead of having a single string, this text writer would allocate more and more as it would be growing for the serializing purposes. Okay, so an additional change would require to have a pool of these, right? To actually have them to allocate them only once and store them in some kind of like a concurrent collection that basically one can use to lease an object and later on release as soon as the serialization is done. And this would have been so much simpler if the call sites hadn't been generated with expression trees. Because to make it faster, what Marten does underneath, for every document type, it creates an expression later on that is compiled, and that's why it is that fast. So as you can count probably parameters in here, that was like around 8 or 10, whatever. Everything beyond 4 is too much. So I went through all these methods generating expression trees and introduced this optimization with the opt-in behavior. So at the very beginning, in this version that was 1.2, you needed to opt in for using this buffer pooling. And was it worth it? Yes, it was. So as you can see in here, the amount of allocated memory dropped significantly. And you can compare the methods for, like the appending events, inserting documents, and bulk inserts, and the time and the number of allocated, the amount of allocated memory after the optimization. So yes, maybe the mean time in this case wasn't was not improved that much, but if you compare the number of allocated bytes, it's okay, around 60% probably. And the case with allocations is following. Yes, they are cheap, But if you remove these allocations from your library, then you basically leave space for other components of your system. And again, these 1 and something megabytes could be allocated by something else without issuing garbage collector. Again, garbage collector is getting faster and faster, but that's the core library for your project, or could be core library. So this improvement really paid off. If we compare inserting documents, the gains are similar. There is a funny story, maybe not that funny, but a story related to bulk inserting, which was, beside actually introducing this pooling, I was able to take the text writer only once from a pool for the whole bulk. So you can imagine, instead of taking the text writer, writing down one document and then releasing it and going back and forth, a whole bulk was basically, or a whole bulk uses a single text writer taken from a pool and released as soon as the bulk is done. If you think what could be a good use for that, if you had another document database and wanted to migrate your data to Martin, that could be a good example how you could use it. The second case I want to mention, and it's Wire or Hyperion, and that's as it's stated in the README on GitHub, a high-performance polymorphic serializer for .NET Framework. And actually, this project could be used to present what a software license is for, because there was a small war over internet when Wire changed its license from a permissive one to like the GNU and all that stuff. But let's keep our focus on the performance aspect. So this serializer shows how much can you gain if you write something from the scratch. And I mean by something, I mean like a protocol designed for actually fulfilling this description. And that Wire or Hyperion, as it's called, because it was forked for aka.net before changing the license, can handle things like versioning or changing schema, or basically it's able to self-describe the messages. So it's quite powerful, and still it's quite fast. So if you wanted to serialize an integer or long or any primitive type in .NET, you would probably use this bit converter class. This is a class inside of BCL, and what it does, it accepts a single primitive type, and it, as I mentioned, it could be integer, long, whatever. And it returns an array of bytes. And here are some stars and unsafe. So admit that you've already lost hope that some of them will appear. Here they are. So this method basically does the following thing. It allocates 4 bytes, then it uses this fixed thing. And fixed is not that memory friendly, because what it does, it pins the memory in this specific region, and garbage collector cannot move it as long as it's pinned. Yes, the pinning is quite short in here, but still, it takes some time. And the bytes are returned. So if we wanted to use these bytes over and over again, this could be helpful, because we would have an array of bytes that we can pass on and on and on and on. But what if this was the case where these bytes are immediately written to a stream or a wire or whatever? Then maybe we could think about reusing the same array, right? Because a single type or a single object can have multiple integer values. So you could pass an array to the first one when serializing the first one, and to the second one, and to the third, and write the result immediately without actually allocating these bytes. So this was my approach in this case as well. So Wire uses the notion of the serializer session, and it's like a context bug or a context object that is passed to every property like the primitive serializer when you serialize an object. And the same serializer session is passed to every single execution of this. And in this case, the change was following. So instead of allocating these buffers, I basically took the buffer from a pool, which was inside of this session, and write the data into it. As this method ends, these bytes are written to a stream or a wire or whatever lies in there. So I don't need to care about releasing these bytes because I knew by the design of the serializer that nobody will reuse them. So I can easily just obtain this buffer from here. The second thing was that if you take into consideration that, for instance, you have a type that has one integer, one long, the second long, the third long, and a GUID property, then you can basically estimate the maximum number of bytes it will use for serializing primitive types. So you can just take max of all the lengths. And in this case, you could pre-allocate only one buffer that will be sufficient enough to go through the whole serialization process. And that was another part that helped in terms of the performance. Again, as lots of code in Wire or Hyperion, depending if you are Akka, if you think about it in terms of Akka.NET or not, again, lots of code is generated in there. So that was again it required playing with IL generator and expression trees and so on and so forth. So now, after losing our faith in this perfect performance and thinking about performance and knowing that we know to measure our gains and measure the real performance of our application, we know how to optimize .NET apps, and not only .NET, but I mean any managed application in some aspects. And it's about time to tell also when it should be applied. So I would say that my role is to always measure first, so write the performance like test or use a profiler. There is, I mean, if you write a test, you can run it multiple times, and as I mentioned, you can put that into your CI environment. So there are some advantages in writing a test. And once you write it, I would say that you should use that only for core components of your application or library. If you write either a shared component, a library, a framework, that's a good place for these kind of optimizations. And these low-level gains quite possibly will propagate for your whole application. As an additional rule, if you make them small enough, possibly the public API won't be changed at all. On the other hand, if you write it in a way that it makes the user to change the way they call your methods, maybe it's actually a good way of making the user of your library writing code according to your standards. So maybe if you introduce that iPool or something, maybe they will use it accordingly to what you meant. And after taking a look how we can optimize .NET or Java, I mean any kind of managed application by removing some allocations, it's time to take a look at the other side, and actually it's time to blame the others as well. So let's take a look at the way how we store our data. And it's quite common that we use just JSON.NET. After all, that's the most popular serialization library in .NET. And actually, probably that's the first step of creating a new project, right? You just create a new project and immediately add JSON.NET reference. After all, that's the best. And actually, it's quite good to have a standard, right? Because that's a standard. But when using JSON, do we always need to use JSON.NET? So there are some disadvantages of using a single library, and especially a popular one. For instance, when you have two different libraries depending on JSON.NET, and one of them depends on a different version. Then you can have a conflict, or you need to write redirects, or you need to use IL repack or IL merge to merge them together, making the result library a bit bigger. So are there any choices if we want to follow this only JSON mantra? Yes, they are. The first is simple JSON. Has anyone heard about it? No one. A few hands. So it's quite an interesting library. That's a very simple library, and it takes only 2,000 lines of code, and is filled with compilation flags. You can configure it the way you want it, and probably, and embed in your library or your project. That could be helpful if you don't want to take a dependency on JSON.NET and you want to have a simple, maybe not that fast, serializer for JSON. The second option is GIL. That's a library provided by a guy from Stack Overflow, and this is crazy fast. I mean, it's like the crazy fast, and it's still a JSON serializer, but what it does, for instance, it takes the memory layout into consideration. So if you, probably all of you know that we've got this CPU cache, right? And there is a thing called cache line inside of your CPU, which is 64 bytes long. And whenever you load something to this cache, or sorry, whenever something is loaded for you, then all the 64 bytes are loaded in there. So if you take into consideration the layout or how an object is put into a memory, then if you read following cells of this memory, it's highly probable that it will be cached for you. So GIL takes that into consideration, making itself even faster. And underneath, it uses quite an interesting library called CGIL, I believe. So it's like the IL generator ++. It helps you with writing a very efficient dynamic code. Okay, but there are some other formats as well. I mean, there is lots of serializers beyond JSON, and most of them are binary. So some of them include some schema, some of them not, some of them are version tolerant, and some of them not. And if you don't know anything beside JSON, it might be a good thing or a good exercise to learn one or two of them. The first one that I wanted to mention is like protobufnet, and that's the implementation of Google protocol buffers that was provided by Mark Gravel from Stack Overflow. And Google protocol buffers, it's quite, it's of course a binary serializer, and the good thing about it is that it's cross-platform. I mean, you can find implementation for anything basically, and it's quite dense, quite fast, quite good. The second thing that I already mentioned is Wire Hyperion. You can use it in akka.NET, but also you can use it on your own. If you want to send messages across different services, that could be a good choice. Again, depending on your requirements, whether versioning, schema should be supported, and so on and so forth. And the last one, Bond, Microsoft's Bond. That's the serializer recently open sourced by Microsoft, and that is used internally. The list of all the serializer is much too long to just mention in here, but these provide quite good examples for this category. And if we want to use these fancy serializers, the first and the most important question is, why do we want to use it and what for? Is it for like a client-facing service or maybe an internal data structure? We need to choose wisely. What about the database? Do you use a regular, like a relational database, SQL Server, whatever, I mean Postgres, MySQL? Or maybe you want to actually serialize data with this dense format and put it in a more like a schema agnostic manner, still using your relational database. And the last but not least, some frameworks are capable of handling multiple ones and doing like the content negotiation. That's a usual case for all the HTTP frameworks, right? Whenever the client sends the types of content they accept. The same could be applied to, for instance, a service bus, which is capable of deserializing multiple schemas, or sorry, not the schemas, but multiple types of messages as well. And that was, I mean, the whole data format thing, it's only an example. Actually, you should think about this as a dependency. And with every dependency your code takes, or actually it's you who take it, you should consider it wisely. Maybe that's the data format that makes your application a bit slower. Maybe that's a logging library or a logger library, or maybe that's something else. But if we are talking about the speed, there is a thing that it's a bit new, not that new, but it's quite helpful if we want to write a good, fast code. And the thing is called, in .NET, it's called async await. And the whole async await may seem as a revolution, but for me, it's a language feature finally providing a tooling or a tool to deal with the underlying asynchronicity. And this is the old way of actually doing the asynchronous stuff. Has anyone ever used that? A few hands. Yeah, good old-fashioned begin-end, right? And the pattern behind it was quite simple. You basically call the begin, send, and then you register the callback, like the old Hollywood way, right? We will call you. And in this callback, you would call and send on this asynchronous result, provide to the callback, and you would run your continuation. The new way of doing it would be to have a method that basically returns a task and await it. And below tasks and below these begin-end methods, there is a thing on Windows that is used for I/O operations. And the thing is called I/O completion ports. And this is quite a powerful mechanism for registering your continuations to be executed after specific task is done. And basically what it does, what you do with your asynchronous call, you just send a message to the I/O. Let's call it the I/O. You send a message, please write to a file. And once the I/O is done with writing, you will be notified and your continuation will be run. So you can see that you don't wait. You basically send a message to the I/O. It's like in a remote server or something, whatever. And then you will be called as soon as the I/O operation is done. And why is it so important to use? So the number of threads that can be executed efficiently on a single machine is quite limited. And it's more or less the number of cores. If you include, or if you take into consideration hyper-threading, it will be maybe a bit higher. And once you breach some threshold, the thing that is called context switching kicks in. And it makes your applications, or especially multi-threaded ones, slower and slower with every thread that is created. The thing with the context switching is quite easy. I mean, if you have 20 threads that need to be run and you've got only 2 cores, then the scheduler needs to put one thread on one core. Then it will be running for like half a second or maybe second, whatever. Then it's taken off. So the whole memory is cleaned from CPU, and another one is placed on the same core. And you can see the context switching, right? I mean, the one thread is removed with the whole memory behind it, and another one is placed at the same place. So what if we left the creation of the threads and the whole management of threads? What if that was handled by the framework? And that's what's done underneath with the async await code and asyncified code. You can think of it as running your piece of code and then sending a message to the I/O and registering a continuation. You could think of your application, instead of having this, to be a thing like the ultimate app builder, right? When you would write multiple then statements that actually do some stuff and then perform this sending the message. So if you compare that to a regular code, the advantage is quite big, because now your code is running your part, then it sends the message to the I/O and your method is done. That's the end. Once the I/O finishes I/O underneath, it will return to you and it will call your callback. And in this case, the callback will be the code underneath the await statement. So as you can see, now we are leaving the thread, we are ending our call, and the thread is ready to pick up another work. And that's how async await works. Basically, you've got a pool of threads that execute your user code. Once it's done and some asynchronous operation is awaited, that piece of code is done. So it's removed. The worker thread is capable of taking another work item from a queue and basically moving forward. So now we see that this I/O is a bit similar to like a messaging or having queues or something, and we could ask, what if we push that to the extreme? And if we push that to the extreme, and if we make this approach for adding to the queue explicit, and we skip all the async await and fancy task-based APIs, you could send like tens of millions of messages a second. And that's the real number. There are frameworks for that. The third one is both dead and mine. It's dead because of the Aaron.NET appearance, but all of them contain more or less the same stuff. Basically, they introduce a very low level queue that you can write to, like in this case, you basically offering some buffer containing a message, hello world, and they are very good and at taking a batch of these messages and doing a thing that needs to be done with them, basically sending them over the wire. But again, making the queues explicit makes it work, because there are no awaits. It's a simple code that basically puts a message to a queue. The thing that it's written in pure bytes and some pointers are used. I'm sorry, that's the side effect. And it could look like this, right? Because if you want to actually squeeze out the performance out of the underlying hardware, that's the code you need to write. Probably you don't want to deal with it on daily basis, but still sometimes this code is required. In the first example, it's like using volatile write to write to this data, and there is of course a star, our beautiful star in here. We take reference and we put one in here just to put the release fence, so it's like the half memory fence. And in the second case, we, for instance, add to some counter, we've got a slot, and we use that to assign some data and finally commit it by storing something to a barrier. It's very ugly and it's very fast. So we know that we can go quite deep, even in a managed language like C#. Oh, and by the way, in Java, instead of having volatile and interlocked, you would just use unsafe class. And it's even better. I mean, you can mess up with much more, with many things. Anyway, so could we resurface? Now we are quite low right now. There are pointers, interlocks, volatiles. Could we resurface, please? And is there anything on the higher level that could be helpful to make our systems more robust? And I call it this thing like the architecture for performance. And I think that sometimes it's underestimated. And in my opinion, I mean, it's the 21st century. And there are still people that think that you can create a well-performing applications sitting in the ivory towers and just drawing boxes. And in my opinion, that's rubbish, and it's totally opposite. If you provide strong foundations for your systems, applications, services, then on top of this you could build quite an amazing implementation, and basically you could let your systems thrive. And let's take a look at this a bit skewed but still a comparison. So my thinking process or reasoning process is that if you think about asynchronicity between processes, it's like the messaging. We already know that with the async await and tasks, if you do the I/O, that's effectively sending a message to the I/O controller or whatever lies underneath and awaiting on the response. So I would compare messaging to this asynchronicity between processes. If you think about this beautiful task when all, so whenever we want to wait on multiple tasks in without actually asking, are you done, are you done, then you could use this, then you can use this task when all and await on the task that is a result of this call. In terms of the processes or sagas or process managers, and I don't want to argue whether a saga is a process manager, let's leave it. I would compare that to task when all. So basically you await on multiple inputs, and once you have them all, you move forward with the completion of your process. And going back to the await, that's like a command and a statement, command and an event, and an event in my opinion. So you send something, the request, you say, okay, I need this to get done, and once it's done, it will return to you, right? I mean, an event, this was completed. With async await and with tasks, it will be just a completion that is run. In terms of services or messaging, that would be probably a handler that handles a specific event that is a result of a command being sent previously. So, wrapping up, I would say that first and foremost, you need to measure your gains. And you need to measure your stuff, because if you don't measure it, you don't know if you have a problem or not. Or maybe if your system is down because it's like dramatically slow, you will know. But we need to measure our stuff, and we need to measure our code. The second thing is actually not about the allocations, but about understanding the managed world. Unfortunately for us, it's like we are blessed with all these allocations and fancy stuff, and we forget to learn how it works internally. I'm not saying that you should know how an allocator works in .NET or Java. What I'm saying is that we need to learn and know how the managed world of our application works underneath. The third point would be that we need to select right dependencies. And I've given you a few examples related to data format, that there are multiple options in there. So the same could be used for logging frameworks or ORM mappers or whatever. Select your dependencies, select right dependencies, and select them wisely. We know that the whole asyncification movement and making everything asynchronous is worth it. I mean, it's actually embracing how the underlying hardware and the underlying operating system works. And basically now it just resurfaced to our language. So it's quite good. The last but one is that we know that we can push to extremes if needed, right? I mean, how many people send like 1 million messages a second? Anyone? Yeah, so it might be not that needed, but still there is an area, there is a potential for actually making that happen if that's needed. And the last but not least, choose your architecture wisely. If you make your architecture synchronous, if you make it without thinking about being reactive, I'm not talking, you don't need to be message driven to be reactive, but you could. So if you don't provide this reactive way of working for your architecture, then you could be hit, you could hit the wall. And with that, that was the performance that I hope that paid off. My name is Szymon Kulec. In the network, I use Kulec as my nickname. And if you have any questions, we've got like 9 minutes left. I drank too much coffee, definitely. I'm around if you want to discuss this stuff as well, so any questions? Nope. So thank you very much.